I'm gonna write down what is this A minus B equal the set of vector A minus B where A is in A is a linear subspace. So if I move my plane by a vector, if I move my plane by a vector, my plane, my affine plane become a linear subspace. It goes through the region. So the analysis of these, more than those, affine space reduces to the analysis of translation of linear subspaces, meaning of linear subspace at the end. So let me derive some more properties. What is an affine? Affine hyperplane. So A. In this case, often you don't speak of affine hyperplane. You simply speak about affine plane. Often. So there exists B such that A minus B is a hyperplane. So for all X, we already know what's the characterization of an hyperplane. Remember, then for all X in A, or even better, let me be more precise. So there, okay, here. There exists C in Rn such that for all y in A minus B, y inner product C equal to 0. But y can be written as x minus b, where x belongs to this affine plane A. So for all x in A, x minus A inner product C equal 0. Can I go on? But x minus A scalar product C, which is equal to 0, is equal to x scalar product C minus A scalar product C. So x scalar product C is equal A scalar product C, which can be written as sum xi equal d I equal 1 to n, where d is simply equal A scalar product C. So this is what the question, my affine plane is defined by a linear equation. Those linear equation I'm gonna find in a linear system. So affine hyperplanes are defined by linear equations. It would be more precise to say by affine equation, because there is this d is different from 0. But since you are used to call them linear system, it's okay for you to call linear equation even those. And this is where I wanted to arrive, because my original system from which I started is what? A1, 1, x1 plus A1, 2, x2 plus A1n xn equal B1. Then A21 x1 plus A22 x2 plus A2n, no, yes, xn equal B2. And another equation, A k1 x1 plus A k2 x2 plus A k n xn equal bn can be also written